What inspires you most at Sega?
What inspires me most at Sega is knowing that everybody at least interacted with Sega technology once today without even noticing.
We are the embedded experts because we have a solution for every embedded problem.
You can see us as a tool provider for other people that also make products. So if you build a house, you need a hammer, you need a drill. We are that kind of company, but for software engineers.
Debug and trace probes, production tools, embedded software and software tools. Our vision is to simplify everyday life for engineers and end users.
People using these products are developers all over the world working with embedded systems. Our market-leading J-Link debug probe is the one piece of hardware that you will find on every embedded developer's desk.
Sega technology is inside everything. Space research, medicine, robotics, motorsports. You can find Sega everywhere.
With our technology, I hope we make people's lives better or easier.
My main motivation is seeing all these projects come to life and change the world or improve the world. Sega is the professional home for so many different people.
Developers, makers, engineers.
What unites us all are three words.
It simply works.
Thank you for a nice introduction. I'm Jacek. I'm going to talk with you about Nix and NixOS for reliable embedded systems development. So this talk is mainly about three different things which go hand in hand. First point is developer environments. Nix is about giving you single command capabilities of spawning like random developer environments. Think about very complex tool chains. Doesn't matter if you need a specific exotic compiler, patch dependencies, whatnot. You can describe it in your repository, single command, boom, that's it. That works without containers and VMs, so it makes it composable. You can mix the development environments of different sub-projects. You can have exchangeable toolchains and dependencies. I will show you how to do that, like spawn the same environment with a different compiler this time and stuff like that. Package builds, so in Nix, you first define the package and then you get the development shell out of that for free. Nix does that differently compared to like Conan or whatever you already know. And you get very nice dependency management with pinning. So think of 5-year-old commits still building like 5-year-olds, like 5 year ago, not like 5-year-olds. You can secure a software supply chain. I also show you how to do that. You can do reproducible cross-compilation much easier than you have been used to until now. And also, if you are building for embedded systems that are like big enough to have a Linux kernel and a process tree, then NixOS is very nice for you because it simplifies system image builds for you in a very composable way. So you can nicely isolate the definition of what you want to run on and where you want to run on and how and stuff like that. I will have a little example for that too. And I will show you what declarative and congruent system deployment means, because that is a completely different way to manage your deployments, be that like live remote deployment or creation of system images. So if any of this is interesting for you, then this talk is really for you. We're not really going too much into depth with embedded bit banging or something. Not at all. One slide about me. In the C++ context, maybe you have seen my name on my C++ 17 book that was released in 17, of course. Maybe you have also lately seen my name in the CT, the German computer magazine, where I wrote a few articles about Nix. So if you missed them and this stuff here is interesting to you, maybe you get to read the articles where we have a very hands-on series of articles that explains how to use stuff for C++ and Rust in cross-compilation context, building Docker images with Nix and so on. got very good feedback for that. And when I'm not writing stuff, then I founded this company with colleagues. We do hypervisors with microkernels for the security and high performance context. Right now I'm still a shareholder there, but don't work there any longer. But the company still does many cool stunts. They just lately ported the VirtualBox virtual machine monitor to KVM. So you can run VirtualBox VMs next to your QEMU, microvisor, and whatever VMs. So this is pretty cool. But for a year now, I'm the CEO of Nixpkgs. I just last week founded it to be a real GmbH to scale it up because the demand has been great. And in that context, I'm helping companies who say, okay, we discovered Nix, we want to use this. It is clearly visible to us that this technology helps us reach some strategic goals, but it's quite a change management problem to get this into the organization. So I give classes and do consulting, and that's the context in which I'm kind of talking about Nix and NixOS. Okay, so about Nix. 20 or actually now 21 years ago, Nix was the PhD thesis of a Dutch dude called Elko Dolstra. And the idea was he wanted to create a way where you can define a recipe, like how to build a specific output, like a package. Here in the background, you see the dependency graph of Firefox. I don't know if this is Firefox or the box up there. However, you can see all the dependencies between there with a nice spaghetti graph. And of course, you will need to build them all in the right order with the right tools in place. And this is quite a management task. If you ever built a Linux from scratch by hand, you did this manually. And I think while doing this, you will have realized that you don't want to do it again, right? Because the thing is to have a way to describe this recipe or this as a recipe and then have the same recipe work on a different computer at a different point in time and produce the same result. This is essentially the same kind of problem that every one of us faces when building software, right? And we want nice ways to do this. There are different solutions. They have all their trade-offs, and this is kind of life, right? The name Nix is actually like Dutch, the word for nothing. In formal German, it's also the word for nothing. And the whole idea is to build complex software from the nothing, right? Because nothing is the point where you start when you first check out a project or something. So 21 years later, what's the results, the practical, applicable results of this research? It's Nix and NixOS. So Nix is arguably a package manager or a dependency manager. The way it defines packages as these recipes that are perfectly reproducible is always source-based. So each and any package that you ever face in Nix, you can build it from source on your laptop. But the packages are expressed in a way and built in a sandbox that makes them very reproducible. So if someone has built the same package with the same inputs already, you will be able to download it from a cache. So it feels practically like a binary distribution because they have a global cache. You can have one in your company too. So it feels like a binary-based package manager, and you can override anything and everything wherever you want, and then it clicks to source-based because different package needs to be built, right? Nix is also a script language. It's purely functional. This is alien to most imperative programmers. I think that is one of the core reasons why Nix is still relatively unknown, because it looks really alien. However, I became quite a fan of purely functional languages in the last 10 years myself, and I see how this is advantageous for the way of package transformations that you want to do here. We also have garbage collection for packages. Why that would ever be useful, I will show you later. Packages can be installed with Nix per user or for the whole system. So Nix works on any Linux distribution. You can install it like right now in your Fedora, Ubuntu, whatever. It also works on macOS and in the Windows WSL, which is essentially Linux, of course. And there you can define, install as a user or with root rights. It can also manage packages individually per shell session. So you can start one shell with Clang, one shell with GCC, or one shell with GCC version 1, another with GCC version 2. And They don't interfere with each other, and it still works without containers. So this is very nice. NixOS is a Nix-based GNU Linux distribution. The cool thing is that you can define the whole system with the installed packages, with the configuration files in place, with secrets management, whatever, from like one big configuration file. Of course, you can split it up into multiple ones for structure, but it's essentially the configuration file explains how the finalized system looks like, which you generally don't have in other distributions. So this also allows you to have different versions of your config and jump between them. So if you deploy something and it doesn't work, well, then you just redeploy the old version, that's it. So this character of having different sessions of same but only similar packages goes up to the system level, and there's also this way of congruent deployment. I will also explain that on another slide. Interestingly, many people ask, like, why is Nix actually so unknown? Never heard about it. When it's so great, why doesn't anyone know it? But that kind of started to change in 2022. So that's a screenshot of the GitHub Universe stream, where they showed the top open source projects measured by the contributors in that year. And suddenly this NixOS/Nixpkgs repository popped up. That is the repository that defines the package distribution. And next to TypeScript, Material UI, TensorFlow, Flutter, VS Code, people are like, whoa, what the hell is this? And suddenly the community started to kind of grow faster now. So if you start to use that in your company, you are still kind of an early adopter, but the conferences now kind of start to grow very quickly. Okay, let's talk about developer environments now. Like, how does that look? Typically, without Nix, you have this world. First day at work, imagine you're an intern or something. You check out the repository. In some companies, it takes a week to even get the authentication and rights to do that. However, you have them, you check out the repository, open the README. And then you need to just follow the 300 steps to massage your laptop into being able to compile this project. Maybe you're using Docker or VMs, but it's still not a single command. And then when it doesn't work, you're like, okay, am I stupid? Did I do one of the 300 steps wrong? Or is the project actually in a bad state or whatever? I don't know. You're kind of dependent on asking the next senior how it's done. And they're like, yeah, right. You need to do this and that. Now we didn't have the time to document that yet or whatever. And then it works. So fine. You will forget that first week of your life and be a productive member of your team now. But then when you get a new laptop or whatever, you need to do this stuff again. And what's even more painful is updating this stuff. So even if you are the person who, updates the toolchain or something, typically that's kind of relatively hard to do because the Docker image or VM needs to be completely rebuilt during that. And then maybe, you get all the other updates too, because the VM from 1 year ago, it doesn't build like this any longer. Docker image also not. And okay, so then you're fixing it for a day or 2 or 3. Of course, maybe the breaking changes also influence your code. It has to be fixed too, so that it builds with the latest stuff. And then you commit that together with the changed README, and everyone in the company has to kind of follow this stuff now. So it's painful, like on the first day. So this is really not good. And this also leads to companies not updating their toolchains often. And the longer you take between 2 updates, the more work you get. If you would be updating like every week, you would only have like small breaking changes all the time that would be digestible. But in the deadline panic and between releases, this doesn't happen like this. Everyone knows it, I think. In the Nix world, it's a little bit different. You still clone the repository manually, but then you just run Nix develop. In the companies where I was helping with Nix, it's kind of typical culture that every project has this. So any project, you just blindly check it out, run Nix develop, maybe wait 10 minutes or an hour, depending on how big the toolchain is and how slow your internet is. and then you can work. And that's it. The cool thing is that all packages that Nix installs in your shell at this point, they are Nix managed down to the C library. So it even installs another C library and anything else between. That means that on Fedora, on Ubuntu, on macOS, you have the same exact versions of everything. So you can really be sure that me checking out this stuff and having it work will lead to you checking it out and having it work. It's all pinned with a log file. So think like a JavaScript or Rust or whatever log file, but for the whole chain of dependencies down to the C library. So even a 5-year-old Nix develop definition will still work in 5 years. So customer calling, sorry, I'm the one who cannot update for 5 years, but I need this CVE fixed. You can actually do it. Of course, you will still build them many, many hours, but you will be actually just working for a few. Updates is easy. You just update the log file. Maybe just in quotes, because maybe it introduces breaking changes. You, of course, have to fix the breaking changes yourself, because Nix won't manage that for you. But you will be able to commit the log file changes and your breaking changes fixes together. So you can atomically jump from working commits to working commits, of course, right? So that is very easy. And because that being so easy, you can actually do it every week. And then the breaking changes come in little steps, right? At least most of the time. So let's demo that. I have a little Linux machine here. I hope the font size is good. Is it readable for everyone? Okay, so this is a little project. Just a little C++ project. It's not exactly embedded, but I tried to have something where we basically depend on some non-completely trivial dependencies like OpenSSL and Boost. Then you see that the executable in line 9, it's called mini SHA256 sum. It's a main CPP file that simply takes a file on stdin and then prints you out the hash. 50 lines of code, just a little example app. It depends on that stuff, and it has an install target, and this is kind of how packages meant to be defined in CMake, right? So on this computer, I have no CMake, no C++, no nothing. When I run Nix develop now, I'm in a shell that looks a bit different. We get GCC, we get... So that is actually the CMake version that already has modules support. I was very interested in C++ modules, seen all the tutorials and like, oh, what the hell are they doing to get a... I just upstreamed this update to Nixpkgs a few weeks ago. It was merged and boom, we have modules support for everyone, like this. However, I'm not even using modules in this example. Then you get the typical dance, of course. So we do CMake -- make, and it builds. Here you can already see that OpenSSL and Boost come from very strange paths. I will explain these later, but you can already see that if I had Boost 182, 180, whatever, they would come from other strange paths. And because you cannot, by accident, calculate this hash, these dependencies, which are explicitly defined, don't interfere with other dependencies that haven't been defined, but are similar and on the same disk. However, so what does this app do? Let's demo this quickly. It does the same thing like the pre-installed. Okay, what the app really does is not too interesting. I just wanted to have something where we can demonstrate static and dynamic linking and cross-compilation later. And the cool thing is that we don't have to manage OpenSSL and Boost ourselves to have specific versions, because that is part of the external package management now. And then we can make our build systems simpler, right? Now, how is this shell even defined? First, we look at the package definition in Nix, because you get shell definitions for free when you have the package definition. And here we can see the first line. This is all the alien Nix language, the purely functional one. And in the top, you see we depend on CMake, Boost, OpenSSL. stdenv, that is the package that contains the C++ compiler toolchain and stuff. So that is a bit more complicated than just the plain libraries. And stdenv has this function make derivation. Derivation is the term in Nix for, so to say, the package definition. This is oversimplified, but we'll do for now. And the package has a name, mini-sha-sum, an src attribute that is the source code. So it points to one folder up because we are in the Nix subfolder now. And from there, it only takes the src and cmake lists folder and file. And that is useful because for the caching later, it would break the caching if the README or the Nix files, if they changed, they wouldn't change the C++ project, right? So you wouldn't want to rebuild. And this is kind of a source filtering facility that improves build times later. Then we have the inputs here, last two lines, cmake boost OpenSSL. Later, when we build this, not in the Nix develop workflow, but in the Nix build workflow, which I'll demo too, that's sandboxed, and you will have only an empty file system with just the dependencies that we mentioned. So this is really cool. Who can imagine why I have native build inputs and build inputs? Why two lines? Cross compilation. We will get at that later. Exactly. So this is the package definition, but it doesn't work alone yet. We still have this flake.nix file. That's the flake.nix file is in all the Nix projects. You typically have this at your project root, and it consists of an inputs and outputs part. Inputs is basically the template where what you will create your log file from. So this Nixpkgs URL, that is the package collection where we get all the packages from. And the outputs define what we are actually providing. Flakes can consume each other, kind of, right? And we say that all the outputs here, they work on x86 and ARM 64-bit Linuxes, but also on macOS. And the rest here defines the packages that can be built and the dev shells. So here we are kind of this packages attribute set. It contains all the packages that Nixpkgs has. And that contains a call package function that simply fills out the parameters that we've seen earlier and then makes you a package from that. And now we can say, oops, let me patch something in the source code. And then run Nix build. So this will create the same build that we had in the developer shell earlier in a sandbox. And then this is the don't care, just build me the package workflow, right? And it's kind of from fresh state. And to get the developer shell, we simply inherited this default thingy from up there because you get a developer shell for free from each package definition. Now let's build a dev shell that is the same like the one before, but with Clang instead of GCC. Here you can see in line 27, this Clang attribute, it uses config packages default like the one from line 21, but then applies an override where we can say this stdenv, you remember it was a parameter in this function before, please reapply this function, but this one parameter needs to be another one. It should be the Clang stdenv now. So that's the package with Clang pre-installed. Let's try that out. When I run Nix develop without parameters, it simply seeks for a default attribute. But now I want Clang. Okay. And C++ is now Clang. Can do the dance now again. Here you can already see that there's Clang. Of course, make still works, but it's will do the same thing. So this is very easy to change this out. And we can actually have like all the package builds with different compilers. Especially in C++, this is useful. Of course, you want your very complex C++ project where it is too easy to write code with undefined behavior. Think about all the juniors and the seniors who don't read enough books. Or slightly standard non-conformant code. You want to have at least your CI build your C++ code with the latest and greatest Clang and GCC and so on. And it is easy to do like this because we didn't change anything in our CMake file, right? It's still the simple one. So this is very nice to change this. What you can also do, there's this make shell function. So we have another shell attribute. And here we can say, well, we want, like in the developer workflow, that is not relevant for the package builds generally, but as a developer, I want additional tools. So for example, make docs to generate documentation from markdown files, package config, whatever debug tools you want, you can just list them. And also inputs from our default package. So it can extract all the dependencies that are needed for your package and mix them with the others. And here you can imagine if we have a C++ subproject, a Rust subproject, and a Python subproject, you can put them into the inputs from things, and then you have the Rust compiler and C compiler and stuff like that in your developer shell, in your day-to-day life available. But when you build the individual packages, they are just built with their individual things in the sandbox. So this is really useful and very nice to compose. You couldn't do that with Docker images. You couldn't say, give me all the packages from these 3 Docker images, right? Okay. Okay, so that was the shell demo. Let's go back here. It's a little bit of a whirlwind tour. However, so maybe you have thought, oh yeah, great, another package manager. I already have 3 installed. Why this 4th one? So it's so great that the packages are so easy to define and so on, but it doesn't help me because we have like 1,000 custom packages at work and I have to repackage them now or what? Or does it have our packages that we are used to from Ubuntu? I mean, this little submarine project that just surfaced up, whatever, GitHub top 10 thingy, does it have so many packages as the big distributions? Let's see. There's this page, repository.org. They simply enumerate what packages exist in which version on which distribution. So that's the address where you get it. The x-axis is the absolute number of packages. The y-axis is how fresh they are by some metric. Of course, you want to be in the upper right. Who uses Ubuntu and so on has more packages than who uses, I don't know, Alpine, OpenSUSE, whatever, right? And the question is, where do we have to zoom in to find Nix packages now? And the answer is maybe unintuitive, but we have to zoom out. So Nix is the biggest open source package distribution in the world that no one knew until now. The reason for that is that by the how the packages are built, how they are defined, how they can be tested, this kind of leads to a distribution where, due to this technology, the ratio of how many packages there can be per maintainer is especially huge. So you can have a bunch of nerds who maintain a huge package collection, keep it extremely fresh without major problems, compared to the effort that the big distributors have to do. So the question, does it have my packages, is answered with yes, most probably. So before we get to the packages topic, the development environment worked without containers and VMs. The reason is that the path environment is simply put together from all the bin folders of the sub-packages, where you have seen they are all stored in individual Nix store folders. We don't have containers, no VMs. You can still run containers and VMs with Nix inside, but you don't need that for at least package isolation. You have like these exchangeable toolchains and dependencies. This little look at override, we just touched the surface of an extremely powerful system. You can patch the dependency of a dependency of a dependency in an override chain, and it's a 2-liner. I have many very impressive examples for that, but not enough time today. You can log file, pin everything in the log file, so even down to a C library. That is why we have the same versions on all the distros. So this is the biggest value add you could have, even if you just use it for the development shells, right? You can commit the toolchain updates atomically with your code fixes, right? So you have working commit, working commit, working commit. And old checkouts work because the packages are so reproducible. Why they are reproducible, we will see soon. Yeah, and that's all the bullet points from this slide. Let's get to package description for development and deployment. As we have seen, we have a package function that simply consumes all the inputs that we mentioned, and then that are given to the package build process. So Nix is not a build system. It calls other build systems. It supports CMake, Meson, blah, blah, blah. Maybe you have asked yourself in this code example from before, when we just mentioned CMake and so on, where does it know what the commands are? That was actually the full package description. But if CMake is in your dependencies, it looks for CMake lists files and knows what to do with them. So there's a huge builder script that's relatively intelligent and can handle all the build systems that you know. Some people have built these things and they work on 80,000 packages. Why not on yours? However, this build process is an offline sandbox. On Linux, they simply use namespaces. So the namespace starts empty. $home is set to homeless shelter as a path that doesn't exist. Then you have all the Nix store paths that are explicitly mentioned in your function mapped in there, no others. So it seems like you have a very small Nix store. This thing is offline from the internet. Time is reset to the 1st of 1970, midnight. And that's your build environment. So you always start from fresh. Also, remember the source filtering that we applied on the package level. So you have really the basic components. Then you are given, the process is given an environment variable that it should use to produce this folder. So it kind of copies all the binaries or libraries or whatever into that. And when it's done, it exits. This is made immutable. So we'll never ever change this folder again. And if you build the package again, it will still give you this folder because it assumes that your builds aren't rolling the dice. Most of the time, this actually works. So sometimes compilers embed a date or a username or whatever into binaries. So that is typically patched out by NixOS, but then you get bit identical results. So currently 99.9% of the ISO image of Nix, NixOS, the installer, I mean, is bit reproducible on different machines at different times. And they are still patching out packages who put some date somewhere. Okay. Then the question is, where does this ABC123 hash come from? This hashes the hashes of the inputs. This is, of course, recursive. So packages depend on packages, of course. And if you change anything, from release to debug version flag to source code patch, whatnot, it changes the hash. You get a different package. So you can build 30 different variants of your package at the same time. For some projects, for example, at the Cypress, the micro hypervisor, we needed the best diagnostics from latest GCC and Clang compilers. Then we also needed to build it with a very old GCC because the customer had that verified. Then we needed new and old boost versions. I kind of created a little Nix function that calculates the Cartesian product of all the combinations as a list, maps the same function over each of those. And then we had like 30 different results that are simply crunched down by the CI. And that was applied on every pull request, so an intern couldn't damage the code. That was very useful because it made interns very powerful with their experiments. Because this process is so generic, you can actually use it for anything. So people build apps, libraries. I typically have LaTeX slides that I built in the sandbox. Images, Docker images, whole VM images, like anything. I mean, typically we are even using this for integration tests. So NixOS has an integration test driver that can help you define multiple VMs, put them in realistic virtual networks and stimulate them each other. And then you check if they do it the right way to test your product in customer simulating situations. And then the result is an empty text file that contains no errors, right? If the test was good. So it's really powerful. And that makes your build infrastructure very simple. You're just running the Nix daemon that sandboxes everything. And it doesn't care if this is a binary or you are assembling configuration files from a script, or if you're running integration tests with 20 VMs, the server just has to be powerful enough, right? So it's really easy. You can do the crazy stuff without ever calling an administrator who has no time for you. Then that was like the look at one package. Now let's look at the chain of packages. Let's imagine this is our package now, and it has dependencies. Of course, you can build a tree. When you look at runtime at our package, when it's dynamically linked, it depends on Boost and OpenSSL. So this would be the set of packages that need to be on the target platform to run there. Nix can calculate you the list of Nix stores that need to be copied over. It also gives you tools to either put it into a tarball, copy it via SSH, whatever. So for the deployment of your complex applications, you don't even need Docker. You can still use that, of course, on top. But for just finding out what needs to be deployed where, you don't need it. You can also compute the build time closure, like what compiler do you need, what C library does the compiler need, and stuff like that. And that is useful because when you do remote builds, that is computed and put to remote builder and build there, and then you get exactly the same results as if you were running at home. What is also interesting, I just painted some of these edges in yellow. These would be kind of the source tarballs, right? I mean, source code is not generated, it's downloaded. You also commit the references with the output hashes, so you can exchange the download servers to ones that you don't trust. And especially customers in the security area, they need to provide proof that their software supply chain is untouched. And this you can do easily with Nix. So you can simply say, please calculate me the list of the yellow edges, put them in a tarball. In addition to all the source code, you basically need a bootstrap compiler. So they have a 30, 40, 50 megabyte, I don't know for sure right now, tarball that contains the TinyC compiler and some BusyBox command line tools from the beginning. From that, they built the real compiler and stuff like that. And then you can put this list of yellow thingies onto an offline server, build it there, and then prove that this set of source code files or folders leads to this binary that you are giving your customer. Typically, that offline build result will be bit identical with your other results from the developer laptops too. And that is very nice. So you can have the very secure software supply chain secured workflows for your releases, while at the same time not sabotaging your developers with ugly workflows on offline machines, whatnot. So they can use the latest and greatest tools, but your release builds will be built in variants and in offline that are proof for your customer. What you can also do is, when you already have this graph structure, you can create PDFs with the software builds of material that print the libraries of everything, like automated. It just drops out of your CI after the developer made the update, like this. Or you can run this graph against a vulnerability database to tell your customer, look, we have like no CVEs, or the one that just pinged up, we already fixed it. So this is really cool. These are many problems where people are still paying a lot of money for or investing a lot of time. In NixOS, it's practically solved. Let's get back to cross-compilation. I think the blue lines are not easily readable. So here on the STD end, I'm commenting in colors that the compiler runs on the build host, but compiles for the target if you do cross-compilation. So we need to inject a different one here. And here it's interesting that when we're building on an Intel machine, CMake needs to run on the Intel machine. It's kind of not cross-compiled at all, right? But OpenSSL and Boost, they need to be cross-compiled because it includes time, at link time, and later at load time, we need the right binaries or files. And this separation makes it very easy to simply call this function with a specialized call package function that puts in the right things. So let's play with that. Connection is gone. Okay. So let's first look at the Flake file here again. In the main branch, I have it a bit more complicated. So we can see here in line 15, that's the normal package from before. And line 17 makes it the Clang package, kind of, right? And line 20 is interesting, that is new. We are accessing the packages.packages static attribute set. So packages is the attribute set which contains all the 80,000 packages. But packages static is the same thing applied with an std env on all the packages, which is parameterized to create static binaries by default. So you get all the packages that you know from packages static and static. Boost, OpenSSL, whatever. But the call package from packages static, it still uses the dynamically linked CMake, so you don't need to recompile CMake to build static packages. Let's try that. So Nix build will still provide the normal binary. Let's look at that result. So that's kind of dynamically linked, as expected. And when we look at the LDD result, wait, let's make it a bit smaller. Okay, you can already see that none of the shared files is found from user lib. So everyone is like pinned to the specific store path. That is why this binary will run on a system where all the packages are installed in other versions too, but with the same versions. When you run Nix build static now, we can see. So this one is statically linked now. And the interesting thing is our CMake file still looks like this, right? We didn't change anything here. And this is interesting because we kind of, with Nix, we are separating with the dependency management tasks and the build system tasks. And it's not the task of a build system to select the right compiler, to select compiler flags like this or something like this. They are all parameters to CMake, Meson, or whatever build system you use. So this is the correct portable way to define and use a build system. And the part that the dependency management parameterizes it always in the right way. It was just kind of undiscovered by all the developers because we never had tools that make it so easy as Nix does. So this is how you unfuck your build system and at the same time get more comfort in exchanging the compiler version or flags. Okay, let's look at what we can do. Otherwise, here, x86 and x86 static and AR64 and AR64 static, they look at packages cross. So in the packages cross attribute set, I will show that later, there are many target platforms. Here is Linux. So these are not really interesting because I'm on an Intel system already, but they also work on the Mac. So we can build Linux images on macOS, not a problem. However, let's look at the ARM thingies now. So these are interesting for us in this situation right now. We are selecting AR64 and use the call package from there. And then we get ARM images. So let's play with that too. So, let's maybe give it some output, which is typically oppressed. So while it's building, we can already see that CMake is called with many flags, where you can see that the right toolchain is kind of injected. So we can stay at this simple CMake file, and then we get, oops. Yeah. The internet connection feels strange here. So it's a dynamically linked ARM thingy. Interestingly, it is easy to run it on this thing because this machine has NixOS installed. And that makes it easy to configure the bin format feature of the kernel. So we can simply run applications like native. Because the Nix store paths, I just have ARM and x86 binaries in my Nix store. Of course, they don't interfere. And then when I run this binary through QEMU, which implicitly happens here, it will simply find the right ARM libraries in the Nix store. So this just works. You can already see that the native one took 1 millisecond and this one is slow. Of course, we can build the static thingy too. And then we get a static ARM binary. What's also interesting is that we can have even more exotic output platforms. So this one is for Windows. We can build Windows exe files with the minimalist GNU environment C++ compilers. So let's do that. Oops. You can already see it stuffs all the DLL files in there. And this is a PE executable. and the stunt from before to just run it locally will even work here, because my bin format also can use wine. So you see all the blah, blah, blah garble output plus the actual application output. This one was again fast because wine is not a virtualization solution. It's just a kind of C library exchanger, so to say, right? So this is very cool. We can run the unit tests of our target platforms if we like. What's also useful, I use this bin format stuff to do so-called ghetto cross-compilation. So if the build system is so bad that, or the project has some clunky edges that make it uncross-compilable, I simply cross-compile it in QEMU on the target architecture, so to say, on my laptop. So that makes it very slow, but it just works, right? So it's very easy to configure build servers like this too, and then have cross-compilation for good and for the bad projects. Okay. Now let's get back to NixOS. So if you are building embedded systems again who run Linux, this is most probably for you. Generally, when you build system images and you build on Alpine, Debian, Fedora, whatever, you get a golden master image kind of, and then you add your changes, and that is your product. The problem is that when you update this thing, there's so many updates inside, you have no control what is updated there, right? So maybe you have to fix many things. Also, this is not minimal. Maybe you don't even need add user or whatever, so you also tend to remove stuff, which is clunky. In Nix, this is different, of course, because everything is built in the sandbox. They even built the image in the sandbox, so you can build it in the sandbox on your laptop. And then you can change the initial config to something else and then build your system image from the beginning, which doesn't contain all the stuff that you never asked for. And you can selectively update what you want. So you have much more control over your own system images. So this has been used in many companies for providing like employee Linux distributions with your company logo on GNOME and stuff like that. It's like 10 minutes of work. Or embedded systems with very minimized and secure systems, whatever. Also, what's cool, this top-level closure. So when you compute the runtime closure of your system configuration, you can create another one. Let's imagine this system is running on your Raspberry Pi right now or something, and you've been building this on your laptop, like cross-compiled, and then you want to switch from one to the other. What you would need to do is you would first transfer, of course, the closure to the target system while the old one is still running, and then you can do an atomic switch, so you just jump over to the other. What happens then is your etc folder is deleted and completely relinked because all the config files come from Nix store. System services are stopped, started, restarted, whatever. And if it doesn't work, but it's still accessible, you just roll back. And if you didn't need step 3, you can run the garbage collection now. So you can compute what parts of the Nix store are not the runtime dependency of what you're running, and boom, your system is minimal again. So this is not even only useful for building images, but also for remote deploying of images that change over time. However, there are also people who use NixOS on embedded systems with A and B partitions, where you say, okay, one system is on that partition, we DD over the new system over the B partition and then switch like that. Nix kind of provides you the mechanisms for all these things, but you still do the design decisions. Okay, on desktop computers, you can already see that grub can store the last n configurations. And if your update broke the system, well, you just boot back into your old one. Or you have a LAN party configuration or whatever. Let's have a demo of that too, and then we're already at the summary slide. So, I thought I will show you this part here. Line 29. Of course, we just built a package. It's a dat package, right? When you want to have it run as kind of a service, I just said, okay, let's run our hashing application on network. So you can connect to a port, send a file there, and you get the hash back, just as a stupid example. and have that in a VM for testing it locally, because I wouldn't need to deploy this to real hardware if it doesn't work in the VM, right? So I said, let's call the NixOS function, and then we put two configuration files into that. One is app-centric and one is platform-centric. So you can later imagine, when we're not running this on a VM, but want to create an ISO image, we would just substitute the second one, and then build whatever we can build from that. So let's look at these files. Let's look first at the VM part. So we say, let's import. So NixOS configurations generally look like this. You describe the system declaratively and it will build that. And behind each attribute path with these dots is some kind of script part that triggers and builds something different. So we are importing the virtualization profile, QEMU VM. This makes it VM. We disable graphics, so we get the VM output from QEMU in the shell, empty root password, and the network port from later will be forwarded to port 8000 on the host. So it doesn't only configure a VM, it also configures how we run it. Let's look at the app part. So here we say services hash enable. So that is our service, a systemd service. Question is, where does it come from? It's from the service.nix file, which I will open soon. We generally, as an administrator of the system, want to say, okay, this service is enabled or not. We open the firewall, where we can also configure what port it uses. This environment system packages thing, you can just list random packages there, whatever you want to have installed. So you can actually mix package installations, service configurations, secret management, and whatnot. And the result of building this is the system that you don't need to touch after that. So it is not uncommon that people describe systems with NixOS where no one can log in. You need no extra security if no one can log in, right? And then the images die after a few hours and you respawn them or something like this. So people do crazy things with that because you can create systems that you don't need to touch after the first build. However, let's look at this service.nix file here. Here we have two parts. The upper half is the declarative part. We define there's an enable and a port option. People who import this can later use service.hash.enable, service.hash.port. It also describes what types that is. So it's kind of type safety. If you mistype a path or put a wrong type into it, the NixOS builder says, nah. Okay, and then when these are used, like if CFG enable is set, then we define a systemd service called hash. This systemd.services stuff comes from other NixOS files again. And here you can see very systemd specific clauses already. You will know those if you ever wrote a systemd unit file. And what we do is we start socat. Socat is an example an application that simply can listen on a TCP port, and whatever it gets, it forwards to SCD and out of a process, what we're doing here. So we tell it to listen on the port configuration and run our application, and then we have it as a network service. So the port stuff again, remember, we can not only set, but also consume things, right? So we have a single source of truth if we ever change the port. Let's run this. Oops. So it boots normal NixOS now. Everything that we didn't set is filled with useful defaults. You can log in. And then we have, it looks like a first-class service. Let's open another shell. We will say netcat port 8000. And then so we feed it whatever file. And then we get the hash back, so it just works over network as before. And that was everything that we needed to write to actually produce a service out of this in a NixOS system image. It might be more work to create an image that works on your target platform with all its intricacies, but yeah, these are the mechanisms that you use. It's very easy, very reproducible, it's very easy to change, very easy to adapt, compose. I especially like this composability of this app-specific config and the platform-specific config, where you say, okay, this is the production config of an app, and it doesn't change on a Azure VM or VirtualBox VM or whatever. Okay. So now I'm through. That's kind of the last slide. We get less customization effort with Nix of packages and also system images. The example that I've just shown is up there, github.com/tfc/ blah, blah, blah. And you can run it right now on your Linux laptop. If you have KVM, you can run all the examples. Okay, without KVM, they will still run, but be slow. But you can run them. You just need to install Nix. You get faster, more reliable updates that are also easier to express and perform, right? You get package isolation in a very nice way. So you don't need Docker containers for everything with all their drawbacks. You can build smaller systems because they contain exactly what you want them to contain. No deltas any longer. This congruent system administration means you are not explaining steps towards your goal, you are explaining your goal. So that's different. That's what no one else does like NixOS does. You get trivial resource cleanup, so you just clean up everything that's not needed any longer. On my laptops, I do that like every 6 months because then I have like more than 500 gigabyte Nix store. And the growth is typically like logarithmically. You quickly reach 100 gigabytes and then you kind of get most of the time overlap again. So you don't need that very often. And the working dev environments are so easy to spawn. It's such a breeze to use. So when we have new employees, first day at work, they git clone, run Nix develop, and oh my God, I can work just like that. Yeah, that's it. That's the value add that I wanted to show you. If you're interested how to do this stuff, we also blog a lot on nixcademy.com. I also have these nice cheat sheets for you. So these are printed on carton paper. Maybe you can just reach them through. If you don't get one of these stacks, then they are over. I have no others with me this week, but you can download the cheat sheet on the homepage too. So just consume them, take them to your colleagues. Thank you for your attention. It was a breeze to show you the nice stuff.
Thank you so much for the talk, Jacek. We have like time for 1 or 2 quick questions. Are there some that we should... Yeah.
Well, you said you won your actual build in a sandbox with an old time and no network access. So how do you deal with commercial build tools that require access to a license manager with the current time?
Oh yeah, that's really painful. What you can do, you generally want to avoid that, but you can poke holes into the sandbox. I mean, you could even use Ccache or something like that. For that, you would need holes in the sandbox that to the outside world. You can do that generally. You can also switch off the sandbox. So you're kind of giving up some of the advantages to deal with some clunky real-life software that exists. Many companies do that. There are solutions that feel really ugly when you once seen the clear things, but it's possible, yeah.
So this seems really cool for embedded systems, but if you already have, for example, a Yocto system, and you'd have a lot of things there, would you have to change that out with NixOS or put NixOS on top of it, or how would you handle that situation?
Yeah, that's, of course, that's a clash of two worlds, like completely. I think you cannot do some feasible thing in between. Of course, you can start with spawning your Yocto environment with Nix to make it easier to build the Yocto image on any computer. So that's a good start. But if you really want to change the system, I think it wouldn't make too much sense to put Nix expressions into your Yocto image. But moving like... rewriting the whole thing in NixOS will be very valuable to you because, I mean, Yocto's strength is building the image, right? NixOS can do that too and give you 1,100 other things on top. So it would be very valuable, but I understand that's quite an investment, yeah.
So thank you so much for answering all that questions.
Thank you.